Okay, so do you have any questions before we start? Okay, so let's, if there are no questions, let's begin. Okay, so last time we talked about UFD. So we saw various properties of UFD, and we saw even a characterizing property of UFD. So it's close to irreducible being equivalent to prime for integral domains. And there's another mild condition that every increasing sequence of principal ideals should be of strictly increasing sequence of principal ideals should be of finite length. Okay, so I don't know why this has come. How do I get rid of this? Okay. Yeah. So, before that, we had talked about principal ideal domain and Euclidean domains and so on. So some special kind of integral domains, which has various nice properties. So now we will go on to doing more general ring theories. So we will talk about how to construct a field of fractions from integral domains. So which is similar to constructing rationals from integers. So we want to construct a field out of an integral domain in the same way as rationals is to integers. And a slight generalization of this process is also called localization. So the name is somewhat strange, but it comes from some geometric consideration, localization. Yeah. So we'll talk about, so field of fraction is a special case of localization. So we will we'll talk about localization, and we'll see that this helps us construct field of fractions from of an integral domain. Yeah. So let's just begin by recalling how we construct Q from integers. So what are rationals? So rationals are fractions. So elements of rationals are denoted by fractions A over B, where A and B are integers, and we don't want division by 0. So we insist that B is non-zero. Yeah? But this is how we represent a particular element, but there are no unique ways of representing a rational number. Right? So for instance, 2 can be denoted by 4 over 2 and so on. Yeah, 6 over 3 and so on. So any rational number will have many representation if we write it this way. So as a set, we'll have to be a little more careful about how we write this set of rationals. So one way to do it is using this equivalence classes. Yeah. So we think of rationals. So to write down the set of rationals, we think of tuples A comma B. So pairs A comma B, where A and B are integers, B is non-zero. So you should think of B as being part of denominator, such that, okay, so this is, sorry, I shifted to wrong notation, such that A comma B is equivalent to C comma D. So A comma B should be thought of as a fraction A over B, right? So A over B is equal to C over D if AD is equal to BC. Yeah, so that justifies this relation. Yeah. So one thing one has to check is that this is indeed an equivalence relation. So we will do that more generally. So right now you just believe that this is an equivalence relation. You can question the set of rationals earlier, then you can believe this. Yeah. So soon enough we will check this equivalence relation, and this relation is equivalence in a more general setup anyway. Okay. So this is an equivalence relation. So we go mod this equivalence relation. That means we consider equivalence classes in this set. In this set, we consider the equivalence classes, and the set of equivalence classes is our rational numbers. Okay. And then we give a ring operation. So we say how we add two equivalence classes. So if we take two representatives and add them and get something and look at that, then we get and look at the equivalence class of that representative, that is the addition. So we will do that in slightly more general setup. And we do multiplication as well. So we define addition and multiplication on this set of equivalence classes, and that makes Q into a ring. And then we will show that it's actually a field. Yeah, if so we can show that every non-zero element has an inverse. And we also show that Z to Q is a injective ring homomorphism. Okay, so we can think of integers as subring of Q, and that completes the construction of Q from Z just by using Z. So not some God-given numbers. Yeah, and then of course. So in high school, you know, you are taught about maybe this process, but then you also are taught about real numbers and complex numbers. So one can construct from rationals to real numbers, but of course that can't be done algebraically. Yeah, so for that you must have seen that in analysis, how to construct real numbers from rational numbers. And then from real numbers to complex numbers is not that bad. That you can do it algebraically. Okay, so this is how we construct all our numbers. So now let's try to generalize this this whole thing to arbitrary rings. Yeah, but before that, are there any questions? Okay, so I guess there are no questions. Seems to be enough people. Okay, so now so we will work with arbitrary commutative ring with unity, and I want to, so what I'll define is localization, and then in special cases we'll see that this localization leads to field of fractions. Okay. So in more general case, what you get is slightly more general ring. So they need not be fields. So the end product need not be field, but it will have some relation with the original ring and with respect to this set. Okay. So let R be a commutative ring with unity, S be a subset of R, then S is should put them here. Then S is said to be a multiplicative subset if 1 belongs to S, and for all x, y in S, x times y belongs to S. Okay. So so this is what multiplicative set looks like. That means it should be closed under multiplication, and 1 should be in S. Okay. So we throw 1 as well. Okay, so maybe we'll start with some examples of a multiplicative set before doing some construction. Yeah, so let's see some examples. So one example is you can take S to be 1 itself. Yeah. So this of course is closed under multiplication, and it contains 1. So R is any ring, you can take S to be 1. Another example is so R any commutative ring with unity. So in this class, any ring means any commutative ring with unity. S you can take it as set of units. So right now, the examples I'm looking at is not very interesting, yeah? So you take the collection of all units in R. Then of course, if you take product of two units, you get a unit, and one is a unit. So this is a multiplicative set. Yeah? So these are not really interesting multiplicative sets in the sense of localization. Yeah? So it doesn't do anything interesting. Okay. Now let's specialize. So see R an integral domain like Z. Sorry, maybe one more example is there, which I forgot. So let's just put this 3. So you can take S to be R2 prime maybe, because this is also not very interesting, but for some other reason. 2 prime. Yeah, S to be equal to R. Yeah, so you take the whole ring itself. So of course, it's again a multiplicative set because R is closed under multiplication and it contains 1. Yeah. So this will also not lead us to something interesting in the localization process. But the third example, which I'm talking about, will give you something interesting. So let R be an integral domain like Z, and so can you give me an example of a multiplicative set in R different from the ones which we have described in 1, 2, and 2 prime?
All non-zero elements.
Yeah. So for instance, in integers, you can take all non-zero element. Product of two non-zero element is non-zero. Yeah, and that is true more generally for integral domain. That product of two non-zero element is non-zero. Yeah, so you can take R minus 0. Okay, so that's a multiplicative set. Okay, and then there is one more example which I would like to say that again.
Positive numbers.
Positive numbers. Yeah. So positive, at least in integers, this is an example. Yeah. So maybe I'll just put in Z. You can take S to be C greater than 0. Yeah. So that's also a multiplicative closed subset. Yeah. Or you can take so another easy way to do it is, so say R is some ring, R any ring. You can take S to be, you throw in 1, yeah, and maybe so let's just show, and X some element of R. So then you can say you want to include X here, yeah. So if you include X, then you want it to be closed under multiplication. So you have to include X square and hence X cube and so on. Yeah, so you consider this set. So this also is a multiplicatively closed set. Yeah, it's a multiplicative set. So in particular, powers of 2, including 1, yeah, is a multiplicative set. Powers of 3 or powers of 4 and so on. And anything else in the ring of integers or more general ring? So okay, so there is one more example which will be useful.
Principal ideals union 1.
Principal ideals union 1 is closed under multiplication. That is true. So yeah, so if you multiply 2 guys, yeah, so yeah, so one can do principal ideals in Z at least, or in any ring, right? Yeah, so maybe this is okay. under multiplication, yeah. So you can also take S to be, yeah. So this okay, R any ring, and S to be, so in fact any ideal union one, right? You don't need a principal ideal. I ideal, and but somehow these are not very interesting. So I'll tell you why. But S equals, so any ring which contains 1 is not a contains 0 is not a, any S which contains 0 is not a good example. So I'll tell you why. So our objective is to invert elements of S. Yeah. And from experience, we know that inverting 0 is not a good idea. Yeah. So we want to avoid sets which contain 0. So that's why I said this 2' is not an interesting example, because it contains 0. And similarly, for same reason, this is multiplicative set. This is a multiplicative set, but it's not going to be very interesting because it contains 0. So we don't want 0 in there, because eventually we want to construct a ring such that elements of S becomes invertible, and so we don't really want 0 to become invertible. Yeah? Otherwise, the ring is not interesting. Okay, so this is so maybe I'll say I'll just say not interesting here, just to suggest that. Though it is not interesting for localization, which is the main goal of studying multiplicative set. And similarly, this as well, not interesting. Okay, so now you give me an example which does not contain 0. Yeah, so we should look for examples which does not contain 0. Yeah. So so one class of my example is which I'm going to write is going to be useful. Yeah, so we'll to study localization. Yeah? So this is let R be any ring. So here any ring means commutative ring with unity. Yeah? And P contained in R a prime ideal. Then of course P is not, but if you look at, and P contains 0, so anyway it wouldn't be, but you can take S to be R minus P. Okay, things which are outside P. So this is like a non-zero element. 0 is a prime ideal, right? So this is sort of generalization of number 3. Yeah. So anything outside 0 you have taken. So similarly, you take anything outside P. If you multiply 2 such elements, it can't land in P, right? Because that is the more or less definition of prime. So maybe maybe we should justify this, that this is a multiplicative set. So this is a one line, it's a tautology, but let's just write it down. Yeah. So AB belongs to S implies AB does not belong to P, but this implies AB does not belong to P. So here, since P is a prime ideal, remember, an ideal is prime if means that if the product belongs there, then one of them should belong there. Yeah. So the contrapositive of that is if A comma B does not belong to P, then their product can't belong to P. Yeah. Which implies AB belongs to S. Yeah. So it's closed under multiplication, and of course 1 does not belong to P because P is a proper, prime ideals are proper ideals, right? So this implies 1 belongs to S. Okay, so S, which is complement of a prime ideal, is a multiplicative set. Okay, and then one can cook up more, but this is enough. This is more or less enough for our for us right now. Yeah. So this will give us enough interesting examples, and maybe a few more interesting examples are missing, but we'll see that a little later. Okay, so one more comment I wanted to make. So for instance, in number 4, we took all positive integers, yeah? So, and our goal is to cook up a ring in which S will become invertible, yeah? So all positive integers will become invertible. So of course, if all positive integers are invertible, then -1 is also invertible in Z, so all negative integers will become invertible. So so in that sense, this example in 4 and this example where we take all non-zero integers should give us more or less the same rings. So we'll see that this indeed happens. Yeah. So S is more or less a tool to construct new rings, but there is no sort of uniqueness and things like that. So we'll see. So once we see the construction, it will become more apparent. Okay. So these are multiplicative sets. Yeah. Any questions? Okay. Okay. Now, let me now define so as I said, we want to invert elements of S. Yeah. So I've written it in. Okay, so I'll stick to a notation which is more standard. So here I should have put denominator first, and let's do it this way. It doesn't matter. Yeah. So yeah, but I'm used to writing it the other way. Okay. Yeah. So I'll write it in the standard way, which is probably what most textbooks do. But there may be some others which don't do, but it doesn't matter. Yeah. So so define define relation on S cross R, where R is a ring, is a commutative ring with unity, and S is a multiplicative set. How do we define this equivalence relation? So S cross R is this product set. So S cross R is this product of two sets, S comma R. Little s is in capital S and R is in R. And S1 comma R1 we say is equivalent to S2 comma R2. So see, I wanted S to be inverted, yeah. So it doesn't match with this Q notation, but meaning I should have put B comma A rather than A comma B. But it's okay, yeah. So forget about that example. Just concentrate on this one, yeah. So we say that these two are equivalent. If so, you left hand side you should think of it as R1 over S1, and right hand side you should think of it as R2 over S2. So if S2 R1, so we want to say that S2 R1 is same as R1 S1 R2, yeah. So we can say that this S1 R2 minus S1 R2 should be 0, yeah. But for some, so here we are working with integral. In this example Z, we were working with integral domain. Here I'm working with some arbitrary ring, yeah, which need not be an integral domain. So what I want is slightly a slight variant of this, which in the case of integral domain and 0 does not belong to S will boil down to this thing, times some S is 0 for some S in S. Okay. So note that if R is an integral domain and S does not contain 0, this is equivalent to saying that S2 R1 minus S1 R2 is 0, yeah, because then S will be a non-zero divisor. You can get rid of it. Okay. So only in some special cases, but it is an important thing when you are working with some arbitrary. So if you are working with integral domain and S is all non-zero elements, you can forget about that question. Okay. So this is the relation. So first claim is that proposition. This is an equivalence relation. So let's prove that, and then we will give, then we'll consider the equivalence classes and give it a ring structure. Okay, so of course S comma R is indeed related to S comma R. So because the second factor here, taking sorry, so maybe S1, let's just say S1 is related to this by taking S in the above setup as 1, yeah, because this says that S1 R1 minus S1 R1. This is it, yeah. So it is reflexive, and the construction itself is symmetric, yeah. So this so this is reflexive. This is symmetric. This is because S1 R1 is related to S2 R2. Then there exists S in capital S such that S times S2 R1 minus S1 R2 is 0, but this implies negative S times, or rather this implies, let's forget about negative here. Negative S need not belong to S, but S times, so negative of this is also 0. S1 R2 minus S2 R1 is 0, which implies S2 R2 is equivalent to S1 R1. Yeah, so this is a symmetric relation, and then finally the interesting thing is that this is also transitive. Yeah, so this is transitive. So this is where, so far we haven't really used that S is closed under multiplication, so that's used here. Yeah, so let S1 R1 be related to S2 R2 and S2 R2 be related to S3 R3. Then we want to say that S1 R1 is related to S3 R3. Yeah. So let's just translate what this means. So S1 R1 is related to S2 R2 means S2 R1 minus S1 R2 times something. So there exists S in, so, and we will need two of them. So let's just write two at one go. There exists S prime in capital S such that S times this is 0 and S prime times, for the other one we have to do S3 R2 minus S2 R3 is 0. Both of them are 0. Yeah. And what we want is some relation between S1 R1 and S3 R3. Yeah. So how do we get S1 R1 and S3 R3? So we want S3 times R1 somehow. Yeah. So to get S3 times R1, we'll have to multiply the first equation by S3. Yeah. And the second equation by S1 and add them. Yeah. So so maybe let's call this 1 and let's call this 2. Okay, so S3 times 1 will have S1, S3 times R1 and S1 R3. Yeah, so this looks okay. Plus S1 times 2. So S3 times R1 plus S1 times the first equation and S1 times 2, S1 times the second equation gives. So what does that give? So let's just expand. So let's just multiply inside. So S times S2 times S3 R1. Let's just multiply it through. Yeah, so I don't have to worry about these brackets. Plus S times S1 times S3 R2 is 0 and plus this one I'm multiplying by S1. So S prime S3 S1 R2 minus S prime S2 S1 R3 is 0. Yeah. So I hope two of the terms get cancelled. It doesn't get cancelled. So I should multiply by S prime as well. The first one and the second one by S. Yeah. So then it will cancel. So let's just do this as well. Yeah, then it will be okay. Yeah, so let's do it in a more. So now the two terms can cancel, I hope. Yeah. Something. This is a negative. Yeah, I hope you guys are paying attention. Yes, I'm making your mistakes and you're not pointing it out. Yeah. So this comes with a negative sign. Yeah. Now now it does cancel. Yeah. Any questions so far? Okay. So then you see that these two cancels out. This term and this term, and what we get is so we can take this S prime S and S2 factor out from this thing, and we get S3 R1 minus S1 R3 is 0. But we know that also S prime S2 belongs to S, since S is multiplicative. Okay. So we get hence. So let's just shift to black. Hence, this is an equivalence relation. So we have showed that S3 R1 S1 is related to R3 S3. Yeah, this is what we wanted to show. Is an equivalence relation. So it's transitive as well, and hence it is an equivalence relation. Okay. Any questions? No questions. Okay. So now I'll define ring operations on the. So now I'll say what our new ring is, the localized ring, and define ring operation as a set, and then define ring operation on that. Yeah. So maybe this is definition / proposition. The set of equivalence classes is denoted by S inverse R. So this set S cross R modulo this equivalence. So that means the set of equivalence classes of this set S cross R. This set we will denote it by S inverse R. Yeah, is denoted by S inverse R. The equivalence class S comma R, equivalence class of containing S comma R, will be denoted by so we want to have a notation which is more reasonable. Yeah, we don't want this crazy notation, and more suggestive, and so we'll denote it by R over S. Okay, will be denoted by fractions looking terms like this. Yeah, so instead of denoting by this complicated thing, we'll denote it by R over S, so that it looks more reasonable. Because this is how we should think of them as well. Something in so R is in the numerator and S is in the denominator. Okay, so this is the definition and a little more. So define or rather maybe define S1 comma R1. Sorry, so I have decided to use this notation, R1 over S1. So this is the equivalence class of S1 comma R1. Yeah, plus R2 over S2 as or rather, okay, so one has to check that this is going to be well defined. So S1, S2 And so this is how we add fractions. Yeah. So this one has to check that this is well defined, because I'm defining in terms of the representative, right? Not in terms of classes. So I've taken the representative R1, S1, R1, and I'm using that, and S2, R2, and I'm using those to define. So maybe the best way to write it is this: the binary operators does. So one is this and this, and R1 S1 times R2 S2, the classes, so both of them has to be shown to be well defined. Are well defined, and maybe I'll since R has already a ring operation, maybe I'll put a different notation. So multiplication in R will maybe denoted by the usual dot, and addition will be denoted by the usual addition, and in this new ring we will denote it by plus circle and dot circle, at least to begin with. Later on, of course, we will use same notation for all of them. Yeah, are well defined. So these two binary operators are well defined. Moreover, S inverse R with this so addition and this multiplication is a commutative ring with unity. So this is a sort of a biggish proposition, so that there's a little more to it. And the map phi, or let's say, give it some name. The map phi from R to S inverse R, sending R to the equivalence class of 1 comma R, yeah, which is R over 1, is a ring homomorphism. Ring homomorphism. Okay. So there are many assertions in this proposition. Yeah. So first of all, we'll have to show that these two operations are well defined. These two binary operators are well defined. Then we'll have to check all the ring axioms for this new set with these two operations, and we'll have to figure out what the unity is. And since we are assuming R is commutative, this is going to be commutative as well. Yeah. And finally, we'll have to show that this map which we have defined here is actually a ring homomorphism. Okay. Okay. So maybe we'll take before beginning the proof, maybe we'll take a break. It's 11:55. So let's reconvene at 12:02 or so. Yeah? Let's take 5 to 7 minutes break, and then we'll begin the proof. Okay, so time to reconvene. Okay, so let's continue. So what we want to do now is prove this proposition. Okay, so okay. So maybe first this binary operator, that plus is a reasonable is a well-defined binary operator. So proof. So let's say there are two guys representing the same class. So suppose R1 over S1 is equal to R1 prime over S1 prime, where R1 prime, and similarly R2 over S2 equals R2 prime over S2 prime, prime R2 prime R in R, and S1 prime S2 prime are in S2 prime are in S. So this these two are equal means that S1 comma R1 is related to S1 prime comma R1 prime, and S2 comma R2, the pair S2 comma R2 is related to S2 prime comma R2 prime, which by the way means this guy, this expression is 0. Yeah, something like this is 0. So we will use this to work through. Yeah. So maybe I'll just write what this means. Okay. So these two statements imply S1 comma R1 is related to sorry, S2 comma sorry, S1 prime comma, I should have written part of this, R1 prime, but anyway, going slow is sometimes better. And the second statement implies S2 comma R2 is related to S2 prime comma R2 prime. Okay. So now we want to show that so if we add R1 over S1, so I want to show, so we want to show that this is well defined, plus is well defined. So what we really want to show is that S2 R1 plus S1 R2 over S1 S2 is S1 S2 is equal to this class is equal this equivalence class is equal to those with primes. Yeah, S2 prime R1 prime plus S1 prime R2 prime over S1 prime S2 prime. So this looks like a complicated thing. So yeah, so the calculation will look a little complicated, but it's not too bad. It's elementary. Yeah. So okay. So let's see. So let's see what these two statements means. The assumptions mean. Yeah. So there exists. Maybe I'll use different notation. U V in S such that. So the first relation tells you that S1 prime times R1 minus S1 times R1 prime times U is 0. And the second one tells you that V times S2 prime R2 minus S2 R2 prime is 0. Yeah, so this is, so we are given these two statements and we want to conclude something like this. Yeah. Okay, so yeah, so let's see what we can do. So you, let's try to work backwards. Yeah. So so let me just write both the things. So this is how one would try to cook up the proof. Want to show that exists W such that denominator of the right hand side times the numerator of the left hand side. So S1 prime S2 prime times S2R1 plus S1R2 minus denominator of the first times the numerator of the second, S2 prime R1 prime plus S1 prime R2 prime times W. So there exists W in S is what is missing. Yeah? So times W is 0. Yeah. So if you want to show these two are equivalent, the same as which is equivalent to saying that this expression is 0. Yeah. So from these two, we have to cook up this this expression. So hopefully this can be done easily. So let's see. So yeah. Yeah. So do I do this? So
If we set W is equal to UV, job would be run.
say that again. W is going to be UV times something something. Yeah.
Just UV works over here.
W equals UV will work. Okay.
Because if you pair the first term over here in the first sum and the last term in the second sum,
then it cancels out. Yeah.
So you know the first.
Yeah, I'll have to yeah. So let's call this equation 1. Yeah, and let's call this equation 2. So if I multiply the first equation 1 by V times something, so what that something should be, maybe S2 prime.
S2 prime.
Yeah. So S2 prime, and if we multiply the second equation by S1 prime times U and add them, then and then if we take W to be UV, then it should work out. Yeah. So let's try to do this, and this should work. Then there will be cancellation. Okay. So let's start. This gives. So let's just write this down. So this is the complicated part. The multiplication is not really difficult to show that it's an equivalence relation. So let's just show this one. S2 prime V U S1 prime R1 minus S2 prime V U S1 R1 prime plus S1 prime U V S2 prime R2 minus S1 prime U V S2 R2 prime. So I hope I have copied it right. Yeah. So the middle term should cancel out. Yeah. I hope. No, this doesn't cancel out. Something doesn't cancel out. Yeah. No, maybe nothing needs to be cancelled out. Yeah. So we want anyway 4-term thing. Yeah. So it's okay. So let's try to see that we can factor out UV and get something like this. Yeah. So yeah. So let's factor out. So everything has UV, so we can certainly factor out UV. And then let's write these two are positive terms, yeah. So and from there we can factor out S1 prime, S2 prime from both these terms, yeah. So let's just do that. S1 prime, S2 prime. So the two positive terms, yeah, the first and the third one. And what remains is, so we have factored out UV, we have factored out S1 times S1 prime times S2 prime. So what remains is S2R1, which is what we wanted, plus S1R2, yeah. And okay, so this is the first one, and then among the second and the third, we have already factored out UV. We will factor out S1, S2. Yeah, so you just factor out S1, S2, and negative of S1, S2. So what remains is S2 prime, R1 prime, plus S1 prime, R2 prime. Yeah. So we get this to be 0. So take W equals UV, which belongs to S since S is multiplicative. Yeah. So UV belongs to S, so U times V also belongs to S. Okay. So so first, so note that this is in the right domain. So S1, S2 belongs to S. So this makes sense. This expression also makes sense. So numerator is in R and denominator is in S. So there we are using S as multiplicative in various ways. So this proves that plus is well defined, and similarly one can show that product is dot is well defined. Yeah. So I'll skip this part. Yeah. So this is simpler than addition. It's because the formula is simpler. Okay. Any questions so far? Okay, so that proves the first segment of it. The second segment is to show that S inverse R with these two binary operators is a commutative ring with unity. Okay, so one has to verify all the ring axioms. Okay, so here I'll use our knowledge of the fact that rationals have similar addition, and it does satisfy all the ring axioms. Yeah. So maybe I'll check a few things, but not everything. Yeah. So next claim is S inverse, or maybe I should do it in a fresh page. So I'm not copying this, but you know, this argument, I hope you have followed it. So I'm not going to copy this. I'll just write the fresh page here. Okay, maybe from here. Claim is S inverse R plus dot is a ring. So there are a lot of things to check. So first thing we have to check is that S inverse R plus is an abelian group. Is an abelian group. So that means we'll have to demonstrate what is, so we have to check that plus is associative. So that I'll not do. So check plus is associative, or I don't know. So I'll just say what one has to check, and then I'll take a poll on what you want to see. And we have to produce a multiplicative additive identity. So 0 of the string. So what will be the 0 element? So we will show that 0 over 1 is the additive identity. Additive identity. We'll have to show that is commutative. Plus is commutative. And finally, we'll have to show inverses, additive inverse exists. So R over S plus minus R. So if R belongs to R, then minus R of course belongs to R. So we'll show that minus R over S is 0. Okay. So this will prove that this is an abelian group. So these 4 things one has to check. Yeah. So let's see. Is there a yeah? So maybe the formula is important. So maybe this is the page I should have kept somewhere in the vicinity. Yeah. So I don't know how to do it very efficiently. But let's just keep the 2 formulas of addition. So we know what the formulas are, but if it's written down, then I can just say just C and you will know. Okay. So yeah. So let's keep this here, and let's move this guy here. Okay. Okay, this is a disaster. One second. Or maybe I should have just fixed this first. Yeah. Taken more time than what I could have done directly. Okay. Anyway. So, so we want to check these. Can you hear me?
Yes, sir.
Yeah. Okay. So we want to check that these axioms are true. So associativity, we know that this is the formula for rationals, addition in rationals. Yeah. So it will follow. So there is some computation you have to do, but it will follow in the same way. So let me just skip the associativity part because that's a little computational. Let's just check that the additive identity works. So R1 over S1 plus 0 over 1 by this formula itself is what we do is take the denominator of the second guy, multiply with the first guy. So it's just R1 plus S1 times 0. So 1 times R1, S1 times 0 over S1, which is same as R1 over S1. Yeah. So this is okay. So that proves that 0 over 1 is additive identity. Commutativity is clear, right? Because if you put R2 over S2 first and R1 over S1 first, the only thing changes is in the denominator S1 S2 becomes S2 S1, and order of addition changes. Yeah, but our ring R is commutative ring. So S1 S2 is same as S2 S1. So there is nothing funky going on. Okay, so it is. So this is also by visual inspection. This is okay. This is okay. This check. And finally, let's just check this last formula. So there should be a circle here. So R over S plus minus R over S by formula, as we should take S times S in the denominator, and in the numerator we'll get S times R minus R over R minus S times R, yeah, which is 0 over SS, yeah. So and then finally we want to check that 0 over SS is same as 0 over 1, yeah. But 0 over SS is equal to 0 over 1. Why? So to check this, what we have to verify, since so with 1 times, so 1 is in S, yeah, so 1 times 0 minus SS times 0 is equal to 0, because every term here is 0, yeah. So that tells you that this is indeed equal to the additive identity. So that tells you that additive inverse exists. So that is just to check S inverse R plus is an abelian group, yeah. Then so that will check that this is an abelian group. Then we have to check that second thing we have to check is that this is associative. But the formula for multiplication is straightforward, yeah. So this is associative, follows from the easily follows from dot is associative in R, yeah. So this was one of the bullets. Second is this is commutative. So we have to check that this is commutative. That again follows, so same argument, easily follows from dot is commutative in R, okay. And what we want to show is that it has unity, yeah. So the candidate for multiplicative identity, what will be the multiplicative identity? So here it was, for additive it was 0 over 1, so for multiplicative it will be 1 over 1, okay. And this is unity, so this one has to check. So and of course one has to check, so the main chunk is distributive law. So this one has to check, and distributive laws. Okay, so this I'll let you check it, yeah. So, and 1 over 1 is unity is again trivial by just looking at the formula. Yeah? R1 over S1 dot 1 over 1 is just R1 over S1. Yeah, because 1 is the multiplicative identity of this guy, of R. So the only thing here you have to check is distributive law in the second set, and that's it. That proves that this is a ring. This is indeed a ring. Yeah, hence the claim. As a ring is a commutative ring with unity. Okay. So, and then the final part of this proposition was that this is a ring homomorphism. So, so let's do this. So this is R over 1. Yeah. So so let's just check this, and then we'll be done. So phi R plus R prime by definition is R plus R prime over 1, but R plus R prime over 1 is same as R over 1 plus R prime over 1. Yeah, because 1 times 1 is 1, and you get this. Yeah, which is phi of R times plus phi of R prime. Phi of R prime. So phi behaves well with respect to addition, and phi of R times R prime by definition is R prime over 1, and this of course again is same as R over 1 dot R prime over 1 by the formula of multiplication, which is phi of R times phi of R prime. Hence phi is a ring homomorphism. In fact, you can also check the so also it's in the stronger sense. Yeah, so also phi of 1 is 1 over 1 is the unity in S inverse R. Okay, so unity also goes to unity. Okay, so maybe this is the right place to stop today. Anyway, we are a little over time. So, so next time we will talk more about this localization process. Okay. Okay. See you Tuesday.